spin at different speeds. That's because they act like fluid, which gets denser towards the core. The interior of the sun is a place of spectacular turmoil. Turmoil that's the key to the sun's magnetism.
The motions there, the convection, the differential rotation, the motion from equator to pole, are driving a new force. They're driving a magnetic field. There's a dynamo at work here, a dynamo that's generating a force that we actually experience here on the Earth.
It works like a giant wind turbine. Churning plasma in the convection zone stirs up powerful electrical currents, which generate a huge magnetic field.
Have upflows here and downflows coming down this way, right?
The holy grail for scientists is understanding exactly how this dynamo generates solar storms. The clue lies deep within the convection zone. Magnetic field lines normally run from pole to pole. But with all the turmoil in the convection zone, that pattern can't last. Rotating layers stretch them horizontally. Convection twists and braids them. Under immense strain, they begin to kink upwards towards the surface.
Imagine this spring is a magnetic field line. The magnetic field inside the sun is amplified, is strengthened by the rotating motions and the shearing motions and the churning motions inside the sun. It wants to expand upwards, and it does, until it pokes out through the surface of the sun.
Tracking invisible field lines is normally impossible. But plasma plays a critical role.
Even though the magnetic field lines themselves are invisible, the plasma, which is heated and hot, can light up along these paths. In maybe the same way, you could think of a highway, and at night you wouldn't see the highway at all, but with the cars with their headlights on, you'd see the path of the highway.
Watching field lines is critical to understanding solar storms. As field lines emerge, they form loops. One end has a positive pole and the other a negative pole. Churning plasma beneath the surface twists these loops, pumping them with energy. If twisted enough, positive and negative parts of the loops cross. When they do, they short circuit with a tremendous explosion. The energy released heats the plasma to millions of degrees, resulting in a spectacular solar flare. It's the final dramatic stage of a very long journey. Photons formed in the core make their way to the surface. Some pass directly into space as sunlight. But in the process, that surging energy disturbs the convection zone, generating a magnetic field. The field lines wind up to the point that it explodes in a solar flare. Now, SDO provides a complete and unprecedented picture as these events evolve.
This is beautiful because the hot gas outlines the magnetic field lines that we would otherwise not be able to see. And here you can see even a twisting structure as some of the mass drains back down to the surface, and a lot of it escapes in the eruption. This is the essence of space weather, or solar storms.
This explains how flares form, but it's not the end of the story. Crossing magnetic field lines can cause nets of plasma to be flung into space. This is a coronal mass ejection, a CME wave. The portrait of how solar flares and CME waves form is coming into focus. But a key question remains. CME waves can travel 93 million miles to Earth in a matter of hours. So what gives them such explosive energy? Part of the answer is hidden here in the sun's atmosphere, the corona. It's made of superhot plasma that blisters at over 3 million degrees Fahrenheit. 300 times hotter than the sun's surface. Some scientists suspect that this heat powers massive gusts of energy that blast CME waves toward Earth at incredible speeds. But why the corona is so hot is an enduring mystery.
Understanding it's essential if we want to get to the bottom of how the sun drives space weather and the impact of the sun on the Earth.
The fact that the corona is so much hotter than the surface flies in the face of physics.
The sun's corona is a very odd place. Take this fire, for example. As I put my hands close, sure, it's warm, but as I pull them away, it gets cold. That's not the case on the sun at all. As you go in close, it's definitely warm, but as I pull away, it actually is warmer still.
Recently, Japanese investigators observe high-velocity jets of plasma shooting up from the near surface. McIntosh suspects these jets deliver heat to the corona, but he doesn't have a way to confirm it visually until he turns to SDO for help.
Lo and behold, we actually managed to join the dots and see, yeah, these objects that we could see moving out of the lower atmosphere at high speeds, kind of like these licks of flame, really were reaching a couple of million degrees. It was really a tumultuous moment. We kind of looked at each other and said, wow, what have we just done?
They've shown that the plasma jets accelerating upwards from near the sun's surface generate tremendous heat. As a result, temperatures in the corona soar to 3.5 million degrees. If confirmed, it represents a huge leap forward in understanding CME behavior. The immense heat of the corona acts like a wind in a raging gale. It's constantly pushing on the plasma draped on the field lines, billowing them out like sails pulling on a mast. Like solar flares, when magnetic lines cross, there can be an immense explosion. In this case, the lines are cut and the sail whips off into space. Loaded with 1 billion tons of highly charged plasma, the CME wave can wreak havoc on electricity-dependent Earth. At the National Center for Atmospheric Research, this violent event is captured by satellites.
Now, to see the CME, we need to create a little artificial eclipse. To do that, we block out the light from the disk of the sun, and that's this little circle here. But what that allows us to do is to see this extremely faint, high-speed thing shooting away from the sun. This one moves at about 1,000 kilometers per second.
By enhancing the picture and slowing it down, it's possible to see the shockwave moving at over 2 million miles per hour. Though we have a better understanding of what causes solar storms and how they reach us, there is still a final pressing problem.
Trying to predict when solar storms are going to occur on the sun really requires a lot of detective work. Basically, we're looking for clues in observations to tell us when potential storms might occur.
The best clue comes from these. Sunspots. Dark patches which can linger on the sun's surface for weeks at a time.
A sunspot is a massive region, several times the size of the Earth, which appears on the sun as a dark spot. It's dark because it's relatively cool compared to its surroundings. And it's cool because the magnetic fields are so strong that they're suppressing the flow of heat from below.
The strong magnetic fields which create sunspots are the breeding ground for solar storms. The challenge is trying to decipher a pattern for when and how many will appear.
As we watch sunspots over a period of many years, we see something very interesting. The number of sunspots at any given time will wax and wane over a period of about 11 years. And since we now know that sunspots are associated with strong magnetic fields, this tells us that the sun's magnetic fields are likewise going through a cycle.
The constant churning and twisting inside the sun creates a powerful dynamo, the biggest electrical generator in the solar system. The magnetic field lines it produces get so wound up that roughly every 11 years, the magnetic poles of the sun reverse. After that, calmer magnetic activity prevails and fewer sunspots form, a period called solar minimum. But because of the sun's turbulent nature, the field gradually winds up again. As it does, magnetic outbursts are far more common, a period called solar maximum.
The solar cycle actually determines the personality of the sun. During solar maximum, it can get very angry and it can throw off solar storms that are sometimes directed at the Earth. And during solar minimum, it becomes much more subdued. There aren't as many sunspots, there aren't as many solar storms occurring. The activity cycle basically determines how the sun is going to act.
Prior to the solar storm of February 15, 2011, things were pretty quiet on the sun. But that outburst marks an ominous turning point. The sun's magnetic activity is winding up again as it heads towards solar max. Just a few days ago, Bill Murtaugh and the team at the Space Weather Prediction Center witnessed the turn.
Arrival of the X2 and the M6, if it comes in with any geoeffectiveness, between 12 and 1800.
So that's what we're seeing.
It's now time to let the world know what it might expect.
Nothing higher than
In the next couple of minutes here, we're going to have to make a decision and make the prediction that this coronal mass ejection is going to arrive at whatever time tomorrow, and the geomagnetic storm will ensue, of course, once it arrives.
With the event we had,
Murtaugh knows that the severity of the storm depends mainly on two things: how strong the CME's magnetic field is, and at what angle it hits Earth's own magnetic field. CME waves approach Earth like a slowly rotating shield. One end is positively charged, the other negative. With magnetism, opposites attract, and like poles repel. If the wave's positive pole lines up with the Earth's positive pole, most of the power of the storm will be repulsed. But if opposite poles line up, the plasma the waves are carrying will hit with full force.
did you say it came in at 115?
114.
Murtaugh makes his final assessment only hours before impact.
It could be larger, more complicated, typically, than just your single coronal mass ejection.
we
so.
nailed the forecast.
Okay. I'd like to think so.
According to the observations, the CME wave will be repelled.
We don't expect it to be too strong. We'll see moderate storming levels, which is good enough to produce some aurora borealis down in the United States, down along the Canadian border, northern tier states, and it will cause some minor problems to the power grid and whatnot.
Space weather for the next